speaker is Soonwon Choi. Soonwon graduated from Caltech in 2012. He did his PhD with Misha Lukin at Harvard, graduating last year, and since then he's been a postdoc, a Miller Fellow at UC Berkeley, working with Norm Yao and Choi. And today he'll be speaking about entanglement phase transition in random unitary circuit measurements, which is also very relevant, I think, if you went to the talk last night, maybe 2 nights ago. Just one more note, so next week there will also be a Q-Farm seminar. So yeah, just watch out for that.
Thank you. Hello, I'm Soonwon. By the way, what was this talk yesterday? It was a related talk.
There's a Google, yeah.
Google. Oh, I see. All right. I'm very happy to be here, and I would like to thank Amir for inviting me and giving me this opportunity to talk about my recent work. Today, I'll be talking about entanglement phase transitions in random unitary circuits with measurements. But I wanted to change the title because as a quantum information phase transition, but that's rather vague and unclear and too abstract, so I didn't do that. But one of the goals is to convince you by the end of the talk that what we describe in this entire presentation is actually about quantum information, not necessarily specific to the entanglement phase transition. So this talk is based on 2 archive papers, and also it's done in collaboration with the graduate student Imu Bao, and the first paper also with Xiao Liang and Ehud Altman at Berkeley. Okay, entanglement is, as we all know, very important and interesting. In quantum systems, say we have a bipartite system A and B, it is possible to have the global entropy being 0. So the entire system is in a perfectly pure state, but still subsystem has an entropy which is larger than 0. And that's very weird because we are throwing away half of the system and you actually lose some information. And that basically means a certain form of the information can be delocalized and then shared between A and B and not accessible, only look at the part of it. That's the quantum feature. And this entanglement is important for the applications. For example, in quantum computations, we know that in the absence of entanglement, quantum computer will not be faster than classical computer. And recently, new phases of matter are being classified as different patterns of the entanglement. And quantum communication and security, of course, like shared Bell pairs are important resource. And quantum metrology, we can achieve the sensitivity beyond the independent non-interacting sensor, like beyond the standard quantum limit, only when we have entanglement. Also for the fundamental physics, it is very important. Here I give you as a particular example, quantum thermalization, and these pictures are taken from a paper by Marcus Greiner. What they study is, they study a quench time dynamics of closed quantum systems. And even though the global system remains pure, if you look at the subsystem, they develop entanglement entropy to the rest of the system. And indeed, this entanglement entropy equals to expected thermal entropy. So it provides a key to the thermalization in the isolated quantum system. In today's talk, I'll be talking mostly about the generic growth dynamics of the entanglement. More specifically, let's consider, say, initially product state, disentangled, unentangled, and consider unitary evolution over time t. We choose a subsystem A and evaluate how this entanglement entropy of the subsystem A, entropy of the subsystem A, grows as a function of time. In the most generic or the case, this is hard to analyze because you need to diagonalize exponentially large Hamiltonian. But using a few toy models, theorists have successfully managed to understand qualitative features of entanglement dynamics. And one of these toy models that's very nice is so-called the random unitary circuit. Here we consider, here I illustrate in 1D, and most of my talk will be focused on 1D. We have an array of qubits initially in 0 state, and we apply random unitary gate acting on nearest neighbor qubit. in this particular situation. So each blue box represents the gate or unitary gate acting on the nearest neighbor and drawn from random distribution in the space of a unitary, independently for every box. Random unitary circuit is in some sense solvable because it has so many nice properties that you can utilize. We have used this random unitary circuit to explain many other dynamical phenomena. But even aside from those technical advantages, random unitary circuit represents a general unitary evolution in a sense that there's no features other than these dynamics being unitary and has some local structure. So if you want to capture the general unitary, probably this is a good starting point. Indeed, there are a number of works that utilize the random unitary circuit to study the different dynamical phenomena, operator spreading, entanglement growth, and the hydrodynamics. These are those papers. And those work actually include studying the entanglement growth in the random unitary circuit. So we partially know the answer to this original question, which means, means the entanglement entropy of any subsystem generally grows linearly in time until it saturates because it caps out the maximum information you can hold in those systems. And the physical intuition is very simple. In random unitary circuit, information gets delocalized and scrambled almost as fast as possible, except it's bounded by the Lycan physics. But is it really true in the realistic situations? In any realistic situations, our system is coupled to a large batch. Therefore, we not only have to consider the information scrambling within the system, we also need to study how information leaks out to the environment. But now, once we open the system dynamics, there are a lot of subtlety comes in. For example, how do we well define the entanglement entropy between the system itself? So there are many, many questions. Generally, there are two approaches to study the dynamics of the open system. And one approach is using the stochastic quantum state evolution. Here, I describe the state evolution of the system. However, the state evolution is not governed by pure unitary Schrödinger equation, but involves a randomness. For example, the environment is creating a time-dependent noise at every time step. And if you repeat the same Schrödinger equation from the same initial state every time, you get a different noise, you get a different trajectory of the wave function. And also, this evolution need not be unitary. For example, the environment could perform a projective measurement that collapses the wave functions. In those cases, wave function indeed collapse and then proceed the evolution. So that's the wave function stochastic picture. Another picture is considering an ensemble of wave functions described by the density matrix and look at how this density matrix as a whole evolve over time. The good example is writing down the quantum mastery equation, generally described by a quantum channel or Liouvillean. Those two pictures are not independent of one another. If you start from the left, an average of all possible trajectories, and you more or less reconstruct the ensemble behavior. At the same time, in quantum, there are ways to decompose this ensemble behavior as a different trajectory, and this decomposition is not unique, but you can still do so. And in quantum optics, this is sometimes called unraveling. In this talk, I'll focus on the first part. The reason being, first part, in some sense, provide the refined information because once you average and then get rid of the detailed information, then you get to the right part. But there are also subtleties coming from this talk, which probably we can discuss as we go. Okay, more specifically, the model system we study is the following. It's basically random unitary circuit in this particular layout. But in between the random unitary layers, you have a projective measurement, a random projective measurement. So what do I mean? After applying one layer of unitary gauge, for each and every qubit, we decide whether to perform a projective measurement or not, with a certain probability P. And in case we decide to perform the measurement, say in the computational basis, like 0, 1 basis, we calculate the expectation value of getting 0 or 1, and randomly sample either 0 or 1 from this probability distribution. Just follow the Born rule, and then once we get the outcome, we collapse the wave function to that particular state. And then normalize back the wave function. And do the same thing for every qubit. And so it's a random measurement, and even for after deciding to measure, still the measurement outcome could be still random, and do that for every time step. We are not the first one to study this model, and this model has been studied by these 3 papers, mostly by numerical simulation. And what they found is amazing the phase transition in this dynamics. So let's be more specific. So what they consider is they start from a product state, they say 0, 0, 0, 0, and then evolve under this stochastic wave function evolution, and then calculate the entanglement entropy of some large subsystem A, usually half of the system, or 1/3. And then calculate this entanglement entropy for each time and measure and average over different trajectories, different measurement outcome, different positioning of the measurement, and then further average over different choices of unitary gate, just to calculate the typical behavior. And then if you plot this entanglement growth as a function of time, they see that whenever the measurement probability is smaller than a certain threshold PC, the entanglement still grows linearly until it saturates a saturation value that's proportional to the volume of the subsystem. But if measurement probability P is larger than a certain threshold PC, and then the entanglement does not grow, but it remains small, and the entire system is characterized by area-line entanglement entropy. So this is the phase transition discovered by these 3 papers. And then my goal in this talk is to understand this phase transition from various, in a variety of different perspectives, inside, outside, like different measures. And also, we'll provide an analytical tool to characterize these phase transitions in a more concrete and mathematical way. So my talk, the rest of my talk is consists of 2 parts. The first part is slightly shorter than the second part. In the first part, I'll basically argue the following statement. This entanglement phase transition is a consequence of competition between information scrambling and measurement. In particular, this information scrambling is essentially a kind of quantum error correction, and this measurement is a kind of error, and this competition between error correction and error leads to the phase transition. That's the main message of my first part. And the second part will describe an analytical toolset to understand these phase transitions. More specifically, we'll show that this random unitary circuit with measurement can be mapped to a classical spin model, actually a class of classical spin models. And the phase transition in this entropy measure can be understood as a phase transition in the spin model. Using this mapping, we'll try to understand at the qualitative level and also quantitative level in certain limit this phase transition from various perspectives, and also present a new figure of merit that identify the same phase transition. By the way, I like answering any questions, so please stop me and interrupt, and then if you have any questions, just raise your hand. Okay, let's get started from the part 1. But before getting to the part 1, let me motivate what. Yeah.
Basically, so these measurements are the basis is not random. It's in the same basis.
You could consider random basis, but because the preceding unitary is random anyway, you can assume it's a computational basis. Yeah. Okay, any other question? Okay, before we jump into the details, let me motivate why I got interested in this topic. In last year, August, Amos Chen and his colleagues published a paper basically saying it is not possible to have a phase transition because steady-state volume entanglement is not possible. It turns out this argument is not correct. However, I think it poses really interesting and important question. So let me recap the statement they made. So let's consider the random unitary circuit like here, and we are to estimate how the entanglement grow at every time step. The entanglement change in each time step can be described by entanglement growth by unitary circuit, and then probably disentanglement due to the measurements. So it's the sum of the 2 terms. And the entanglement growth is actually bounded by order 1 number. Here, log small q is a dimension of the local Hibas dimensions. For any bipartition, say, cut in the middle of the chain, the number of gates, only the gates that across the cut can increase entanglement between this part. Therefore, every time step entanglement growth is limited by order 1, or the area in the general dimensions. On the other hand, every time step, we are measuring extensively many qubits or qubits. And those measured one, after the measurement, is completely disentangled from the system in the product state basis. So wave function will be some unmeasured part end up completing the unmeasured basis, and they contribute 0 to the entanglement. Therefore, if you have some general notion of entanglement density gamma, and then probability is p, for the half chain, you generally expect to reduce this amount of entanglement. And this is proportional to the size of the volume L. Therefore, if you believe in these rate equations, and then set the steady state condition where the entanglement entropy equals to 0, and then we expect the entanglement density has to be 0, because on one side, we have a volume scaling, the other side is area scaling. This computation is not fair at all. One is volume, one is area. We always know thermodynamic limit, volume is larger. Therefore, there cannot be a phase condition. However, this expectation is contradicting to the numerical simulations that's done in the previous work. So what's going on? So we wanted to understand this question, and turns out just clearly understanding this particular or answering this particular question actually teaches a lot. So for that, we consider a toy model. So let's start with a very simplest toy model. Here we consider a bipartite system, left and right, divided by this dotted red line. And initially, this left and right shares gamma times n bell pairs. The large n is supposedly a large number, and gamma is some number, a fraction from 0 to 1. Let's say 0.2. And then on the left, we also have a disentangled, initially unentangled 1 minus gamma times n qubits or qubits, so that total on the left we have n qubits, on the right we have gamma times n qubits that show the bell pairs. And on the left, we apply random scrambling unitary among this entire Hilbert space. On the right, it doesn't really matter, we just apply some unitary. It doesn't actually change the argument at all. And then what happens is we randomly choose a certain fraction. The position doesn't really matter because it is scrambled anyway. And certain fraction f, and then perform projective measurement on those guys. So I'm going to call unmeasured qubits as A, and those measured qubits as B, and the rest of the other side as C. So before B part gets measured, the entanglement entropy across this cut is equal to the number of initially shared bell pairs, because the scrambling unitary or any other unitary cannot generate any more entanglement. So the key question is, now we measure an extensive number of qubits on the left. Does it actually reduce the entanglement across this cut or not? And the answer is not necessarily. Sometimes do, but under certain conditions it does not. And when it does not, that's the question. And this problem can be almost exactly analyzed by using so-called the decoupling theorem. And this is one of the elementary theorem in the quantum information theory. But the intuitive understanding is very easy. So we consider the conditions where the fraction gamma and fraction f is tuned so that gamma plus f is less than 1 minus f. The physical meaning of this is, if you are to consider the subsystem B and C together, that's less than half of the system. So that the remaining part is only A, so that the B and C is smaller than A. In these conditions, if you compute the reduced density matrix between the B and C together, rho BC, actually they factorize. They can be written as rho B tensor product rho C, and some corrections that are exponentially small in n. Remember, this condition, this inequality condition, is actually coming from this exponent being negative, because if it's negative, it goes exponentially small in n. So what does it mean? It's actually very simple. In this case, from the C's part, it's maximally mixed because we have the reduced estimate for the C is maximally mixed. And the global system is pure. And on the left, it's maximally scrambled. So this entire wave function is a representative state for the Ha random vector. So it's globally pure, but if you look locally, it looks almost like infinite temperature ensemble. Especially if you consider the subsystem that's less than half of the total system, it looks like maximally mixed state because it's maximally mixed. So if this B and C and their composite system B and C is actually less than the total system, together it looks like a maximally mixed. And in the maximally mixed state, in the infinite temperature state, any 2-point mutual information is 0. Because of the mutual information is 0, it's if and only if that the density matrix factorizes. In other words, this B and C know nothing about each other. So B does not contain any information of C, and C does not contain any information of B. Therefore, performing any projective measurement or even any unitary operation or POV or whatever you do does not affect the reduced density matrix of C. So it's an information theoretic argument. So whenever this condition is satisfied, so entanglement reduction is bounded by this exponentially small factor. So the information cannot be, the entanglement is not destroyed. Is everything clear at this point? In some sense, this is like 1/2 of my talk. So I want to make sure this is really clearly delivered. Yes?
So if I took some bits in A,
yeah,
by that argument, these bits would have no information on C.
That's
just
right.
because there's only 2 bits, and together with C they have on the right. But at the same time, I know that there are bell pairs connecting them.
Yeah.
So how does that square together?
So the reason why it works is if you choose any combination of a certain fraction f, it knows nothing about C. Only when you take them together. So any portion, no matter how you choose, like all like n choose, k cases, it does not information any C because this bell pairs is completely delocalized. Only when you have a non-local information jointly together, then you can reveal the correlation on C. So that is
because of the scrambling.
Because of the scrambling. So actually, that's a perfect question for my next slide. If you actually don't scramble, but use like permute is random qubits, and then measure a certain fraction randomly chosen, with a probability f times gamma, we hit the bell pair and then destroy the entanglement. So this argument does not work. It works only when this unitary is like scrambling. The information is non-local way. So the bottom line of this part is this scrambling unitary is hiding or protecting the correlations between left and right or C from being revealed by measurement, any local measurements. And this is essentially the error correction mechanism. And this connection to the quantum error correction can be made more seriously. So I'm the same diagram, but I changed the notation slightly. And also, by the way, this UNE doesn't play any role, so I just dropped it. So our input state is some wave functions where you have a gamma n pair, bell pairs entangled with some reference system. And then you bring a bunch of ancilla so that the total number of qubits is n. What you know is I'm going to send this information to somebody else, but during this process, something noisy will happen for the fraction of qubit. Therefore, I encode this information using this ancilla qubit in a certain way, such a way that even if you have an error happen on a certain fraction, you can still recover the bell pair or the coherent information with the C. Okay? So here the question is, okay, then how much coherent information with the C can be transmitted in the presence of this the fraction measurement of f? That's the well-defined question. Actually has a name, and this is a defining statement for the quantum channel capacity in the quantum communication. The quantum channel capacity is defined by the amount of coherent information characterized by IEC that's maximized over best encoding scheme you can do, given a certain noise model Fn. And what is this coherent information, IEC? The coherent information is also pretty simple. It's given as a 2-term. The S input is the amount of the information you encode in the initial state. In this case, your initial state is here. So the entropy of this system is basically gamma n because it's entangled with the reference. Minus mutual information between this input state, or now we can rely on the reference because it's the same thing, to the dephasing environment. And the dephasing environment is not drawn in this picture. The meaning is very simple. We consider the total information and subtract the amount of information that is revealed by the environment, and that's the coherent information.
What's the environment?
Here, the environment is a dephasing. The dephasing path that I did not draw here. So when we describe the measurement, you can model it as if those measured qubits are coupled to another bath, and this bath is like dephasing this degrees of freedom. So those bath is environment. And what we showed in this paper, actually it's not a very complicated thing, it's just like 2 lines, but math is not very illuminating, is that this coherent information equals the entropy of the subsystem A averaged over different measurement outcome in D. So this averaged entanglement of subsystem A is exactly what we're looking after at the beginning of this talk. Equally, this is the average of entanglement of C, average of the measurement outcome. If the measurement fraction is very, very large, eventually we'll reduce the entanglement. Nevertheless, this average behavior equals the coherent information. What's very well known in the communication, the quantum communication field is that if you choose this encoding unitary to the random unitary, it provides one of the best encoding schemes. So in some sense, by choosing the random unitary, you can protect the information in the best way. And actually, this random unitary encoding is asymptotically saturates the upper bound that you can achieve in a given quantum channel. Okay, indeed, this very related situation has been considered by Michael Gollans and David Hughes with different motivations at the beginning. So what they have done is this. They now consider a mixed state evolution. Instead of the disentangled, unentangled the product state, they consider the maximally mixed state as an input. And then consider the trajectory picture of this random unitary circuit with measurement. And this maximally mixed state can be considered as some state that's initially entangled with the reference. Now this picture is almost the same as our previous one, except that now unitary is interspersed with the measurement rather than at the very end. What they evaluated is after sufficiently long time, they evaluate the entropy of this entire system on the left, and they show that there's a phase transition. In the measurement is less than PC, the entire system still remains impure, so that the entropy of the global system is proportional to the volume. There is some coefficient alpha. But if measurement probability is larger than a certain number PC, it approaches to 0. And this phase change then means the global system approaches to pure state. So for this reason, they call it the purification phase transitions. Now that we know that the coherent information equals this average entanglement of the global system, this phase transition essentially also implies that there is a phase transition in the quantum channel capacity. Okay, we can go a little further. So we devise a new model where instead of a qubit, we replace a cluster of m qubits. And instead of the single unitary gate, I have a smaller gate circuit in one box. And also whenever we measure a certain p fraction of qubits within this each cluster. And this model is more controlled than the previous model because we can independently tune the degree of scrambling by the depth of the local gate D and the measurement rate P independently. Our expectation is because of this random unitary within the box, we are repeatedly encoding the information in each cluster. And in the limit that this M is much, much larger, each cluster will support some alpha fraction of logical bits. And those logical bits will actually develop the entanglement over the long time, so the saturation entanglement entropy will be proportional to whatever the volume times the fraction of the logical bit that's supported in this system. And this alpha is basically quantum channel capacity per qubit. We did a numerical simulation using the Clifford gauge, and what we see is this 2-dimensional phase diagram. When D is small, we do have a volume node to area law phase transition. But if you increase the degree of scrambling, indeed the volume node phase becomes larger and larger because we better protect the information within each cluster. So it's a quick and nice check. So the summary of the first part of my talk is that, okay, we have a phase transition and also purification phase transition studied by Michael Gollans and David Hughes. And they are originating from the same physics, which is a phase transition in the quantum channel capacity. And the underlying physics behind this quantum channel capacity is this competition between the unitary information scrambling that hides information from the environment versus a certain rate of projective measurements. Okay, so any questions so far? And now let's move to the second part. Second part is slightly more technical than the first part, but I find it also more exciting. Here we will provide an analytical tool to study the entanglement phase transition. More specifically, as I said before, we'll map this random unitary circuit with the classical spin model. The mapping random unitary circuit to a spin model has been done in the previous work. But here we're generalizing their method so that we include the effect of the projective measurement, which could be potentially non-local. And then from this exercise, we'll learn, we'll be able to see this phase transition in yet another perspective in terms of Fisher information. Okay, the first step to the mapping is modifying our projective measurement into the wing measurement. So here previously, we randomly decided whether to measure or not with a probability. But in this case, we deterministically measure every qubit at every time step, but we measure in a wig way. So we perform the wig measurement. So what's a wig measurement? So if we have a cartoon picture, there's a larger version of a cartoon picture. So in the wig measurement, each wig measurement, what we do is the following. We introduce a fresh ancilla qubit prepared in a predetermined state 0. And then we couple those qubits with one of the system qubits that you want to measure, weakly measure, by some unitary coupling. And then for this talk, I'm interested in performing the classical type of measurement. I don't care about so I projectively measure. Therefore, I assume this ancilla is immediately dephased, eliminating any coherent information that could be encoded in this ancilla qubit. So that means it's a local classical measurement. And then if you actually perform projective measurement ancilla, and then this is the type of wig measurement. We can think of this ancilla as an actual experimental apparatus, the measurement device, which is like a large microscopic object, so it dephases very quickly by the rest of the universe. But in this talk, I'll talk about even more specific type of wig measurement. So we assume the system qubit has a Q internal state, and we assume this ancilla measurement apparatus qubit has a Q+1 internal state. And then the coupling is controlled rotation. If the system is in the state I runs from 1 through Q, your ancilla qubit gets rotated from 0 to a state I. So the ancilla is enumerated from 0 to Q, so total Q+1 state. After dephasing, this ancilla is measured in their computation. And at this point, what happens is, suppose you measure the ancilla and you find that the state is in I, and I is not equal to 0. That means your system qubit must have been in the state I, because that's the only way that you couple 0 to the I state. So measuring I on the ancilla implies that the system is in I, so that equals to measurement. But if you measure a 0 state in ancilla, it does not learn anything about the system. Therefore, it's equal to not performing a measurement. So in this formalism, and this particular choice of the wig measurement, our random projective measurement is equal to this particular case. And we can actually mathematically show by computing the quantum channel. And the probability of measurement, P, is characterized by the degree of rotation alpha, by this relation P equals sin square alpha. And in general, we can consider different generalized measurements for the mapping to a spin model. And turns out this formalism makes us very easy to analyze the problem. So that's the first ingredient. And second ingredient, remember the yeah?
Can you go back?
Yes.
So when you say the ancilla is immediately dephased,
yeah.
Are you doing some explicit, so first you couple the system to the ancilla with a unitary operation like that R.
That's right.
And then are you doing something non-unitary in the ancilla?
Yes.
Before you projectively measure it?
Yes, actually it turns out doesn't matter, because if you projectively measure,
that's already,
it doesn't change, it includes the dephasing. So.
Right, so you don't have that, you don't need that separate.
That's right,
But if you had to do it, it would be something like taking the off-diagonal entries of that reduced entity.
Exactly.
Setting it to 0.
Yeah, so I'm not gonna talk in detail, so let me just mention here why I put this. In principle, if you don't dephase and then keep the ancilla, and remember we are bringing new ancilla every time and qubit. At the very end, you could perform some non-unitary among the ancilla and then perform measurements. And that's why we call it quantum measurements, because you utilize even the coherent information and delocalize the information. In this case, we can prove that there's no phase transition. The reason being, information scrambling protect the information only from the local measurements. But if you accumulate information and do the joint non-local measurements, the scrambling cannot be helpful. But I'm not going to discuss that in detail here. So that's the reason for the dephasing.
So I think I missed it. Why is this weak? What is the weak part of it?
That's just name. So if alpha is small, it's a weak strength of measurement. But weak measurement in general, like talks about this formalism. You don't measure the object, or you measure some ancillary object that's coupled, partially coupled to the system. So it's just name of the formalism. Weak measurement formalism.
So this has been introduced to distinguish between when it is dephasing locally versus globally, either
Yes.
in on the top.
That's right. Yeah. Oh, dephasing depends on the basis, like local basis.
Right.
Okay. Okay. So previously we've been interested in calculating the average entropy of the subsystem, averaged over the different measurement outcomes and the positions. And in this weak measurement formalism, we now introduce this new figure. So we have a random unitary circuit, and we have a bipartition A and B, and we collected all the ancillaries accumulated over time as this orange box. And this average entropy is just exactly equals to conditional entropy. Conditional entropy of A on the measurement apparatus M. In some sense, this is trivial because what we really mean is the entropy of the system A, given that we have some knowledge about the measurement outcome, right? So this is just equal relation, and this equal sign is true only if you use this von Neumann entanglement entropy as an entropy measure. So our job is to describe the phase transition in this conditional entropy, now averaged over a different set of unitary gates, including here. Okay. And here we need to introduce three key ideas. The first key idea is so-called replica technique. So usually we are interested in the quantity of this form. We have the von Neumann entropy of some reduced density matrix, average over unitary. But this von Neumann entropy involves taking the logarithm of the matrix and then take the average outside the logarithm, which is mathematically very hard to keep track of. So instead, we introduce a cousin to this quantity, enumerated by different n. So n could be any integer. And defined in this way. It looks scary, but if you zoom in, actually it's a very the simple object. We take rho and then raise to the power n. And then take the trace. So n equal 2, it corresponds to purity. N equal 3, it corresponds to the third moment. And then average this quantity over unitary gauge first, before taking logarithm. And then we get a number out, and we take the logarithm and just normalize by n. Therefore, this is much easier to handle at the theoretical level to calculate than the average of logarithm. And what's more nice is if you take analytic continuation of n goes to 1, this expression reduces to this, including the ordering of the averaging and the logarithm. Therefore, our approach is to evaluate S of n for every n, and then later on we get analytic solutions, and then take the limit n goes to 1 to calculate the von Neumann entropy. For these practical purposes, we only need to calculate this nth moment, because the rest is trivial calculation. The second idea is real heavily used diagrammatic tensor network representations. So for example, a density matrix, rho ij is a matrix, and you have a two index ij, and they can be described by two indices. And the unitary acting on two qubit can be described by this four lag tensor, the qubit on the left, qubit on the right. This is output of the state. And let's do a little bit of exercise with the tensor network representation. Suppose you want to take the trace of rho, and we are just contracting those two indices together. If you want to calculate the trace of rho squared, you consider two copies of rho and contract column and row indices across, and the same across. So I think it's very fairly easy to understand. If you want to take a partial trace of the joint system rho AB, we only contract the indices that's associated with some subsystem B, but not the other. Okay, I think it's very clear. So let's apply. By the way, I said the three key ideas, but only have two items because the third item is coming up later. So it's not hyper. So let's apply this to our random unitary circuit. We consider this circuit initial state random unitary circuit accumulated ancilla, subsystem A, B, and measurement across M. So now, ideally, we want to calculate this conditional entropy averaged over U. But as I said, we'll consider its cousin as 2. So let's stick to n equal 2 case as a special because it's easy to understand. As a two-term, the entropy of A and M together, and then subtract the entropy of M. Right? So we have got two terms. This is what we've seen before. And then for illustration, I'll only focus on the first term for now. So Again, it looks scary, but actually it's a very simple object. We want to calculate the trace of rho AM squared. But what's rho AM? Rho AM is obtained by partially tracing out B. So what we do is we start from the total density matrix rho, trace out B to get the rho AB, and we multiply, so it's a square, and then trace for the rest of the degrees of freedom. So is this equation okay? Actually, like understanding the technical details is not very important, but I want to make sure the general outline is delivered clearly enough. So let's write down this object in the tensor network diagram. So we know our wave function after time evolution is described like this. And then, but we need the density matrix. We have a bra and cat partner, so we have another conjugate partner to write down as a density matrix. Now this object is a reduced density matrix. We want to have rho AB by tracing over B. So we'll contract those two lines like this. So we get the rho AM. And then we need to now square them. So we consider another copy. So we do two copies of them. And then we do the multiplication and the contraction, which can be written in this way. So it looks a little frustrating, but this is what it is. This is a fairly simple procedure to do. Okay, so what we know is this object, trace of rho square AM, corresponds to this tensor network representations. But this representation can be simplified. So what I'm going to do is with a diagram, I'll just fold it by half like this, and then fold it another time by half, so that the blue boxes are on top of each other, and the orange boxes are on top of each other. And that diagram, that diagram looks like this. It's much clearer. The only difference is now, for each index M, A, B, we have 4 indices. Those 4 indices are originating from bra vector, cat vector, copy 1, copy 2. So we have 4 lines. And then remember, this unitary circuit is actually not a single unitary. It's made out of multiple gates like this. And also, this accumulated ancilla is actually originating from the ring measurement in every step, in time step. So we can absorb them as a part of the network like this. So this network, the blue box represents 4 copies of a unitary gate acting on 2 sides, U dagger, U dagger, or copy 1, copy 2. And the orange box is whatever the contraction associated with the ring measurement procedure. Okay. Here I want to draw one attention to the top boundary conditions. Here we see that depending on the subsystem A and B, those 4 lines are contracted in a different way. And that's because we are calculating this particular object AM, we are tracing B first within each copy, and then trace over A across 2 different copies. Therefore, that's represented as a different crossing. So that contracting across different copies and contracted within the copy for A and B. Okay. So actually, even though I presented a lot of diagrams, I didn't do anything. So I just said this object can be written as this diagram, and if you evaluate this diagram by summing over all indices, then we are done. But can we evaluate this tensor contraction? But unfortunately, the answer is no. And it's not only that I cannot do that. If you can do this, then the quantum computer is not useful, because contracting this network is almost as powerful as actually performing the quantum computations. But we have to use a different idea. The different idea is the following. Instead of taking the contracting, we'll just take the average over unitary gauge first. So that's the third idea. So without evaluating this network, I just take the average at the diagram level. So each unitary gauge appears 4 copies on top of each other. And we evaluate the average tensor, the average of those tensor among the all set of unitaries. And turns out this tensor can be evaluated and has been evaluated in the math literature by using the representation theory. And nicely, it decomposes in this form. So first, we have a tensor, 2 tensors, like up tensor and then later down tensor, tau tensor and the sigma tensor. And they are decoupled. There's no line of those 2. And also, this tau and sigma could take 2 different classical values, plus minus 1. And depending on the value, their content looks slightly different. But first of all, from the fact that they decompose, already we see that if you replace this tensor for every unitary in our entire network, this entire network will factorize into smaller pieces. So the contraction is tremendously easy because we only calculate the local contraction. But the cost is we have to sum over different possibilities of sigma and tau weighted by this coefficient. And this coefficient is so-called Weingarten function in the math literature. Okay, furthermore, actually this content of the tensor is extremely simple. For example, if the either sigma or tau is +1 value, take the value. And this means you contract within the copy, and there's no value associated with it. And whenever it's minus, you contract the lines across two different copies. So let me recap that those 4 lines represent the Brian cat and copy 1, copy 2. So those lines basically means how you contract them within or different across copies. So with that in mind, we do the calculation. So we start from this object, and then we place every average tensor by sigma and tau. And this arrow means averaging over unitary space for every gate.
Is this changing the order of the averaging in the very first expression? Or
No.
No.
Because it's a linear operation. Yeah, this whole thing is already rho square, so we are taking the average of this whole thing. So the order doesn't matter. The cost is you have to sum over all configuration of the sigma and tau, but at least for a given sigma and tau, we can evaluate this rate very efficiently by locally contracting this network. And we can further simplify this one by integrating out this tau variable just explicitly. And then we indeed get essentially a partition function of the Eisenstein variables defined in the triangular lattice. So after these whole procedures, we have mapped this particular quantity as a partition function of a spin 1/2, the classical spin model defined on the triangular lattice with the Hamiltonian. And this Hamiltonian has a respect to Ising symmetry. And the parameters of coupling, say J1 and J2, are a function of our ring measurement strengths and the local Hilbert space dimensions. And those calculations can be done exactly. So I'm not presenting the expressions. And now, still evaluating the exact partition function, we haven't done it, so we still don't get the value out. However, we can talk about the physics more intuitively because the spin model. Namely, this Hamiltonian exhibit the phase transition as a function of you tune the J1 and J2. So if you tune the local Hilbert dimension goes to the infinity, that corresponds to going to the 0 temperature. And at the low enough temperature, those one exhibit a ferromagnetic phase. And if you measure too often, say measurement probability is near 1, or the local Hilbert dimension is very, very small, and then this spin system goes to the paramagnetic phase. The spins is up and down disorder. Okay, so far we have evaluated one term on these gates. How about the second term? The second term is almost the same as the first term, except that we do not have this A. So the change is actually the same spin model, except that the top boundary condition is now changing. So previously we had a part that's contracted across the two copies. So that's represented in minus, consistent with the tensor over the bulk. But in this case, the A also has a positive because A and B are equal to one another. It's also trace order first. So they have the same spin model with the different boundary conditions. And also remember, so we are taking the logarithm of the partition function, which is basically the free energy. So this whole expression means the free energy difference between the two spin models where everything is the same except for the boundary conditions. In short, this S2 represents excess free energy originating from having two different domain, having a domain wall and the boundary. Okay? So what's going on? So in the weak measurement strength, the spin model is described by the ferromagnetic phase. In this case, having a particular minus boundary for the subsystem A inevitably creates the domain wall, and the domain wall is costly in free energy, and then their size of the domain wall length is proportional to the subsystem size A. That's why this quantity trace rho A B square, log of that scales the volume law. But in the paramagnetic phase, when the measurement strength is very strong, the domain wall condensates, and then there's no the extra free energy cost associated with this behavior. Okay. Any questions so far? Yes?
So your justification of the replica trick is that you don't have any disorder? So what justifies using replica trick?
I did not justify it. So here, it's, so we have took the n equal 2 here as a special case. We'll talk about n equal generally n. Eventually, we'll take the limit n goes to 1. But turns out, you can take this limit only in a special case. In special case, which I'll describe later. Yeah, and also, in that sense, it's not fully justified, but you're absolutely correct. This model is translation invariant, and there's no reason to behave, any self-averaging behavior to kick in. Yeah. But at the math level, I did not prove this. Okay, and this intuitive picture generalized to arbitrary choice of the spin model n. If you choose different n, we get a different spin model. So I could move on to the different general case of n, but before doing that, I want to elaborate a little further about how we can look at different phase transitions with the same spin model. So let's take this Michael Golan's and David Hughes purification phase transition. We start from mixed state and measure the global entropy. The only thing that we change is we change the initial state from the pure state to the maximally mixed state, and then we don't measure the subsystem entropy, but we see the global entropy, average over measurement outcome. In the spin model, this modification corresponds to different bottom boundary condition, and this change corresponds to different top boundary condition. The bulk behavior will remain the same. So in the end, we get the same spin model, and then our cousin to the condition entropy looks like the free energy difference between having these two different scenarios of boundary condition, either positive, or minus and positive. So this is the domain, the excess free energy of unequal top and boundary conditions. In the ferromagnetic phase, this unequal boundary condition inevitably forces you to have a domain wall in the middle, and that's the large entropy in this phase. In the paramagnetic phase, again, the domain wall is not costing free energy, which is fine. Besides yet another, we can play actually many more things. So here I want to present one more example. So here we consider two different initial states, either psi 0 or psi epsilon. And psi epsilon is close to psi 0 except that it's locally perturbed by one side, by an angle epsilon. And then we do not look at the system wave function, we just trace it over, we are not interested in it. We only look at the classical measurement outcome probability distribution. We denote them in P0 and P epsilon, and try to see whether they are different or not. So the goal here is, can those two different scenarios be distinguished by only looking at the measurement outcome probability distributions? This is very relevant to metrology. You choose a small parameter, and can we distinguish from a certain set of measurement outcomes? So yes, we can quantify the distance between these two probabilities as a so-called KL divergence in the classical literature. In the limit that epsilon is very small, you can rewrite as a, the perturbatively the second order term. The leading order always vanishes because of the positivity of the KL divergence. And this coefficient F is so-called the Fisher information. And this Fisher information characterizes how much information about the initial quantum state the measurement possesses. And this formalism is very different from what we have described previously, because it does not look at any system wave function, only measurement outcome. We do not need entanglement measurement to do this. And this is in some sense totally complementary, literally complementary, because we are from the perspective of being an environment. We are using the information revealed to the environment. And our expectation is, when the measurement probability is less than PC, the information is fastly scrambling. So this Fisher information won't be large, because you cannot extract the information. But when measurement is probability large enough, you can extract probably large amount of information because we are interrogating more often. So we use the same trick. We consider the cousin of spin model. And for the special case of n equal 2, the quantity of interest maps to the free energy difference for two different cases. Both cases, we have a pinned boundary condition positive. But one case, we have a boundary field epsilon. The other case, we do not have an epsilon. So we consider the free energy difference between the two. If we expand it around epsilon, that's just measuring the bottom magnetization. So the Fisher information is basically bottom magnetization given that the top boundary condition is pinned. In the ferromagnetic phase, the memory of the top boundary survives to the bottom, so the expectation is 1, so that this whole thing goes to 0. In the paramagnetic phase, it's random, so this quantity is the average 0, so the Fisher information goes to 1. So as a function of measurement strength, we expect a phase transition by this. When measurement strength is sufficiently weak, it's a paramagnetic phase. When it's large, it's a paramagnetic. Ferromagnet, it's a paramagnet is saturated to the maximum value. So what it means is, if the measurement strength or the probability is sufficiently small, some information is never revealed, even if you infinite for a long time. And that's the long range order in the spin system. But if you measure strongly enough, within the finite time, characterize the correlation length in this phase, you reveal the maximum classical information that you could have gotten from the measurement, from this measurement outcome. So to summarize, because time probably we just recap. Yeah. So this is like 3 different parameters, like bipartite entanglement, or the purification transition, or Fisher informations. They all map to the spin model. Only difference is the top and boundary conditions. Because of time limit, I don't want to go into the details for the generalization to the end. But the rough idea is something that you can already imagine. We consider that n copies of the unitary and average together, you get this classical spin variables that enumerate how you permute the contraction of the different copies. And the boundary condition also describes how you contract the different permutations of copies. And then eventually you get the spin model where each spin variable has an n factorial state describing different permutations. And then otherwise, whatever the quantity of interest remains the free energy curve of having different boundary conditions. In the special limit, this is like Ben's question. So in the special limit, turns out the local Hilbert dimension goes to infinity. It's all model for every n reduces to standard parts model, a parts model with a different number of internal states. And this internal state is n factorial. And also the bond is vanishing in leading order. Therefore, it's a square lattice. So 2D square lattice parts model with the n factorial internal state is exactly solvable. And the phase transition point has analytical solutions by Kramer duality. And then we can evaluate those and then take the analytic limit and n goes to 1. And in this picture, we can also study the universality of these phase transitions. If you consider the 2D sphere lattice parts model, and the state goes to 1, and this limiting behavior is equal to the bond percolation. So we believe that the entanglement phase transition in the von Neumann entropy belongs to the universality class of the percolation transition. But I want to emphasize that this whole limit works only when the Q goes to infinity, like very large bond dimensions. But at the finite Q, the universality class of the phase transition is not justified. So here, the justification was replica technique, replica trick. At least it satisfied disorder constraint and so on, but it's constrained by the parameter region, local Hilbert space dimensions. Okay, I want to finish up my presentation by summarizing this slide. So this is a summary of the first half. So from the quantum system perspective, we have a phase transition described by entanglement change or the purification change, and we saw that they are described by quantum channel capacity. But there's an alternative perspective, a totally complementary perspective, characterized by the amount of information that's revealed in the measurement outcome about the quantum system. And they are related by the competition between the information scrambling and then the measurements by the environment. And we talked about underlying the theoretical framework by mapping the model to the spin model to understand this phase transition. Finally, this is a few outlook and an ongoing project. Turns out our mapping to the spin model, as Amir pointed out, it's related to the Google supremacy protocol because we can estimate for those people who knows, like there's so-called the linear cross entropy benchmark, and that quantity is trace of rho square. So that's something that we can evaluate very efficiently by using the classical Monte Carlo, even in 3D, at high depth. So that's something that we are working with in collaboration with Umesh, and also the phase transitions and entanglement phase transition, the integral system. I'm aware of that. Vedika is also interested in this. We are with collaboration with Norm about long-range interacting systems, and more broadly, I would like to establish some connection to the quantum chaos with this entanglement phase transition. Thank you very much.
So you've defined the quantity as n for n equals 2, and then we calculated for n equals 2. And then you show that calculate differential 3, 4, and so on. Right? But these are all integers, and then you go to limit n to 1. What meaning does that even have?
I don't know, to be honest. No. So n-state part model or k-state part model means like you're spin with a k internal state. So, and then people can write down a partition function for the k-state part model. Take the limit that k goes to 1. That means you can take one state. But it's not.
It's not even defined for a fractional n, right? So
it's not even defined for values. But what you could do is once you write down an expression for the partition function, it is some function. You can reparameterize this partition function, and this you can generalize the integer to the whatever the real number, and then you can analytically continue this argument.
So, okay, so it seems that measuring this entanglement phase transition. So, are there any proxies or diagnostics of entanglement phase transition which are more efficient to measure in some in-principle experiment? I mean, so suppose that you could actually run these quantum circuits, for example. Now, it's actually very difficult to measure the entanglement. I mean, like when you talk about averaging over these measurements of the state with a large number of qubits, that's like very impractical. But is there some proxy, some probe, or whatever it is that would allow you to see the space transition without making an extensive number of measurements, maybe exponential?
That's an excellent question, and I've been thinking about it for a while.
Can you repeat the question?
Yeah, so the question is, I haven't talked about how to experimentally probe these entanglement phase transitions. If you want to do it in the lab, what should you do and what should we measure? And measuring the entanglement is actually very expensive, so probably that's not the right way to do it. Can you define some two-point correlation function or some physical observable that still identifies the phase transition of this type? So that was the question in my understanding. And that's a very relevant question. I thought about it quite a while. But to be honest, I couldn't find anything.
Sure.
And I'm suspecting that it's fundamental and fundamentally difficult. The reason being, I want to convince that what I do is a phase transition of quantum information. And roughly speaking, this is something that I need to justify in the future. I believe this volume of phase is a phase transition into the classically non-simulatable dynamics. The areal of phase is more like the dynamics can be simulated by classical computer.
Yeah.
And by definition, if you want to prove that something is not classically simulatable, you want to show something that Google has done, for example, like you do the brute force calculations of large scales.
Sorry, actually, I think there's a simpler reason. I mean, can I ask if this is correct? Which
Sure.
is that the way that you're thinking about these measurements, where you make these projective measurements and end up in a pure state, those are most naturally described, if you want to think about how many measurements you have to make, by quantum channels.
Yeah.
Whereas in this projective measurement scheme, you have this stochastic variable, which is like, I mean, you're not actually considering, how do I say, the incoherent sum over all the possible measurement outcomes when you look at a particular instantiation.
That's right.
So is somehow the tension between the fact that when you make measurements, you really need to average, you need to really do the quantum channel point of view, whereas in this, to see the phase transition, you need to kind of look at it from a single instance?
No, so I see your point. That's an important point, but actually I don't think that's the right explanation.
Okay.
The reason being, down to earth, this is a question. Like, so suppose you do the random unitary gate and the projective measurement.
Yes.
You want to average the entanglement of the final resultant state. In order to measure the entanglement, there are certain ways, say randomized benchmarking or the swap test.
Yeah.
You need to repeat the measurement, but next time you perform the evolutions, the measurement that you perform during the time evolution have a different results.
I see.
Therefore, you cannot reproduce the measurement outcome.
Right.
In other words, you have to measure so many times so that this random outcome is happen to be agreed.
Right.
And those incidents has to be large enough so that you can average enough for the measurement of entropy.
Right.
And that's the difficulty, yeah.
So there was a paper addressing this in the last month by Mike Collins and David
Yes.
Hughes,
Yes.
where they were getting around exactly the problem you're
That's right.
mentioning, and they
That's
said that this transition can be measured
That's right.
in a physical observable setting
That's right.
without running into the exponential
That's
bottleneck
right.
that you drop.
Yeah.
How?
Yeah, the problem is, so they argue that this is kind of, let me paraphrase in my language. So you study a certain, you put the information and basically measure whether this information is revealed or not. Suppose you have an efficient algorithm to decode the information, so you know what to look for. And you can do the calculation with the classical backend. And that's possible for the Clifford evolution.